Okay, hello everyone. This is Mr. Boyce, and you have made it to the end of the year. So we are getting ready for our final exams, and this is the first. We have unit 7 to 14, and this is our first unit in chemical reactions. So just to kind of give you an overview, I'm going to do each unit as a video. I'm going to give you answers in a range. So it is your responsibility to finish the math out. You will get credit for the work, assuming you have the actual answers and not just the range that I'm giving. And please round to two decimal places. So let's go ahead and get started. So first part, Unit 7, what we're mostly concerned with is identifying and balancing reactions. So real quick, let's just kind of go over the different reaction types. You've got your double replacement. This is going to be two compounds, like right here, and they're going to swap ionic partners. So we are going to get into predicting in a couple of ones, and we'll go more into how to do that. You have your single replacement. And so this is something like here where you have a compound and a metal trying to break apart that compound. So again, switching positives, but this time you have a single element breaking apart a compound, or at least trying to. So for single replacement, look at the activity series. Oops. And I'll show you what that means in a minute. From there, we have combustion. And remember, the combustion of a hydrocarbon, like here, where you have carbon and hydrogen, is always going to react with O2 to form CO2 and H2O. This is one of those things you just kind of have to know. It won't always be told to you in a question. After combustion, you have synthesis. And so this is going to be smaller compounds forming larger ones, makes sense. And also decomposition. And decomposition, basically, and the easiest way to put it, is smaller things making larger things. So with that out of the way, you might want to put some notes for that. I'm going to go ahead and erase this and get started on the questions. So first off, what I want to do is balance these. Now you really want to pay attention to this because notice my polyatomic, my cyanide stays the same on both sides. That's awesome because that means I can think of it as one thing and I don't really have to pay attention to what it's made of. Also, the BrO3 also stayed together on both sides. So instead of trying to balance the bromine and the oxygen individually, I can think of it as one thing. Now you can choose to write them out like this: GaCN, SN for 10, and BrO3. What I like to do is just go left to right. So after this one, that's what I'm going to do. So gallium right now, I have one on the product side. Okay. So I have one right here, and I have one on this side. So cool. I'm going to move on. Cyanide, I've got three because of this three right here. So very important that I notice that. And on the product side, I have four. So I'm going to have to come up with a number that both three and four can divide into evenly. And let's see here, 4, 4, 8. Uh, oops, sorry. And so to do that, what I'm going to do is I'm going to divide this side by 3. So 4 times 3 is 12. That's the smallest number they can do. And on the other side, I'm going to multiply by 4 and give myself 4 of these. So 4 times 3 is 12. So I have 12 cyanides on both sides. Now that did mess up my gallium, but I'm not going to worry about that right now. I want to go through all of them first and see if that corrects it on its own before I go back and try and fix something. Okay, so next I've got 10 SN right here. And on the product side, I have 3. And on the reactant side, I have only 1. So that's not going to work. I'm going to put a 3 here. So I've got 3 on each side. And then for the bromine, I've got 3 right here. Remember, this 3 applies to everything that's in the parentheses, very important. And over here, I've got 4 times 3, which is 12. So I'm going to need to put a 4 here in order to have 12 on both sides. Now, like I said, I did change some of my numbers, so I'm going to go back to the beginning and double check and make sure everything is working out for me. And for the gallium, right here, I've got 4 because of the coefficient. And over here, I also have 4 because of the coefficient, so that's good. Cyanide, I've got 4 times 3 is 12. And on the other side, 3 times 4 is 12. So I got 12. For the tin, I've got 3 on this side and 3 on the other side. So that's good. And for the bromine, 4 times 3 is 12. And 4 times 3 is also 12. So this is balanced. Uh, that's kind of the longer way to do it. I'm going to go a little bit quicker with the other ones, but there you go. Reaction type, this is a double replacement because I have 2 compounds. Okay, next I have a combustion reaction because it's a hydrocarbon reacting with O2. So first thing I'm going to do is I'm just going to go read this as a sentence from left to right. Carbon, I have 2 on this side and I have 1 on this side, so that's not going to work. I'm going to put a 2 here. Now my carbons are good at 2 apiece. Hydrogen, I've got 2 on this side and 2 on this side, so for now, hydrogen's fine. Now, oxygen, I have O2. I can do whatever I want to that, and it's not going to affect my carbon or hydrogen. So I'm just going to go ahead and count the oxygens on the other side first. And you got to pay attention to both of them because here I have 2 times 2. So I have 4 oxygens in CO2, but I have just 1 oxygen in water, which is 5. And I can't really make O2 work out to be 5 unless I were to put, let's say, 2.5, which is not a thing. I'm not allowed to do that. But what I can do is double it. So I'm going to double this to 5. This would have been 1. I'm going to double this to 2. This 2, I'm going to double to 4. And this 1, I'm going to double to 2. And if you go through and count that, you're going to have 4 carbons, 4 hydrogens, and 10 oxygens. So everything will balance on both sides. Next, I have a single replacement reaction. So I have a compound and I have a metal. Now with these, what I need to pay attention to is this even going to happen? Is iron strong enough to break calcium away from its bond? And so I'm going to go into my periodic table and formula sheet, and I want to know, is this even a thing? So here's my activity series, and you get to use this on the test. So iron, let's see where you at, iron. There we go. And I want to know, is that stronger than calcium? Where is calcium? Calcium is all the way up here. Okay. And so that means that calcium is higher on the activity series than iron. So in reality, this wouldn't actually happen. It's just not strong enough to do it. But all we're doing is balancing it. So let's just go ahead and balance it anyway. So let's see here. Okay, so calcium, I've got 1 here. Whoops. I've got 1 here and 1 here, so that's good. NO3 is nitrate. Okay, and I've got 2 of those here, and I have 3 here, so that's not going to work. So 3 times 2 is 6, and 2 times 3 is 6. That's my lowest common denominator. So I'm going to go ahead and put that in there. Next is iron. Now I have 2 irons here because of that new coefficient. So let's drop a 2 in here. And then let's just double check everything. Calcium, I now have 3 because of that coefficient. So I'm going to have to balance that out with 3. But then nitrate, 3 times 2 is 6. And 2 times 3 is also 6. So I'm good to go. And iron is 2 to 2. So I'm good. And this is a single replacement. Okay, here we have a decomposition. So I have 1 compound breaking down into 2 different compounds. First thing I want to do is count my irons. So I have 1 here and I have 2 here. So Let's put a 2 there. Make sure even that all out. Hydroxide. I've got 3 hydroxides, and over here I don't have any hydroxide, so I can't think of this as a polyatomic ion. I'm going to have to think of this as one atom at a time. So let's start with oxygen, but I still have 3 oxygens because I have 3 hydroxides. So on this side, I have 3. Oh, wait a minute. What did I do wrong? I have 3 hydroxides for every iron 3 hydroxide, but very important, I have 2 iron 3 hydroxides. So I don't have 3 hydrogens and 3 oxygens. I have 6 hydrogens and 6 oxygens. Okay, so here I have 6 oxygens and here I have 1 oxygen. Now, if I try and add to the iron oxide here, then I'm going to end up with 7. That's too many. So I'm just going to put a 3 here, and that gives me 3 oxygens right here with the iron hydroxide, and then 3 with the water. And so that's 6, so that works out. I still have 6 hydrogens, and because I put my 3 here and I have 2 for each one, 3 times 2 is 6. I have 6 hydrogens as well. So this all balances out at 1, 2, 1, and 3. So this is a good time to point out if you're going through and doing these and you put the wrong number down and you get frustrated and your balance isn't happening, the best thing to do is just cross it out and start over. Don't try and fix a bad balance. Just start all over. Okay, now what we're going to do is we're going to start predicting our own reactants. Now, seems hard, but it's not terribly hard. But let's look at some very important things here. So first off, I want to break this into its individual ions just to see what it is. Now, lead, this is a variable charge, so I don't know what the charge of lead is. It could be 1, 2, 3, 4. It could be whatever it is on the test. But I do know hydroxide. Hydroxides, that's on my list of polyatomics. Okay, and that's got a -1 charge. So that one I do know. And I know that I had to use 4 -1 charges. So therefore, this PB must have been a +4. So this is lead 4 hydroxide. Hydrogen and chlorine, a little more straightforward. H plus and Cl minus. These are charges from the periodic table. So hopefully you know how to find those pretty easily. Okay, so I'm going to put these together, and to do that, you can kind of put them in either direction, but most people will do the outers first. So positive always comes first. Lead with a +4 charge, chlorine with a -1 charge is going to go together as PbCl4, and then I'm left with H plus and OH minus. Now, because, let's see here. And so that's going to form HOH or H2O, same thing. Okay, next thing I want to do is balance the reaction because that's what it's asking me to do. And here, let's start with lead. I've got 1 lead here and 1 lead here. So lead's good at 1. Hydroxide, I've got 4 hydroxides here. And on this side, because I wrote it as HOH, I can think of this as just being hydroxide. And I've got 4 on one side. And now I have 4 on this side. So if you have hydrogen and hydroxide in your reactants, it really helps to write water like this. It just makes it much easier to balance. Okay, so good. Let's see, your hydrogen that's not part of hydroxide. I've got that right here. I've got 4, and here I have 1. So I'm going to put a 4 here. And then I'm left with chlorine. Now, because of this coefficient, I have 4 chlorines. And this is where the importance of making sure that you do your swap drop. This PB with a +4 charge and the Cl with a -1 charge, if I do my swap drop and reduce, I get PbCl4, which is what I did. if I didn't do that properly, this would not have balanced properly and it would have been very frustrating. So if you're balancing and you find you get stuck, you probably did your swap drop and reduce wrong. That's easily the most common mistake to make. But we didn't make that mistake, so this is relatively easy. So there we go. Okay, and this is an acid-base reaction. This is a strong acid and a strong base, which will always form a salt. Remember, salt's not just the salt that you put on your French fries, it's a metal and non-metal ionic compound. And then water. Okay. So this is important to remember. An acid-base reaction, a strong acid and a strong base will create a salt and a water. Okay, lead oxide, lead and oxygen. Now, again, what do I actually call this? Oxygen is always a -2, so this went together 1 to 1. This must be a +2, so this is lead 2 oxide. Now, if it was PbO2, right, then I would have two oxygens, both -2, which would be -4, and that would need lead with a +4 charge. But that's not the case. This is 1 to 1, so this is lead 2. So see, in this case, I had lead 4. In this case, I have lead 2. Although that may not even matter because we want to know, is copper even strong enough to break up lead? So let's take a look here. Okay, and let's look for copper and lead. So here's lead and here's copper. And so notice lead is higher on the activity series than copper is. So therefore, copper is not strong enough to break apart a lead compound. And so this one here, will this reaction happen? No. And I know this because I looked at the activity series. So I really don't even need to do that. Okay, this is a combustion reaction. So that means it reacts with O2 to form CO2 plus H2O. So this is very important with a double or single replacement or whatever. You can look at those, break them into their ions, just like I did here, and recombine them in the correct way, and you're good to go. But with this, you kind of have to know what it makes, or it's going to be a lot harder. Excuse me. So to balance it, I don't have hydrogen and hydroxide in my product, so I'm just going to write water as H2O. Carbon, I've got 3 here, and I've got 1 here, so let's put a 3 there. Hydrogen, I have 8. All my hydrogens in the oxygens are in the water, so I'm going to put a 4 here. 4 times 2 is 8. Hydrogen's good. O2, I can do whatever I want to that. So let's find out how much oxygen there is all together. And in my CO2, 3 times 2, this is 6 oxygens plus 7, 8, 9, 10. I have 4 in the water. So 10, I'm going to put a 5 here because 5 times 2 is 10. And I am good to go. These are my coefficients. Okay, Mg3 and 2 with potassium, special K. Is potassium stronger than magnesium? Stay tuned. Let's find out. Okay, here's magnesium. And I don't see potassium. Oh, there it is. Sorry. There's potassium right there. So yes, potassium is stronger than magnesium. Therefore, this is going to happen. And so I'm going to break this apart into ions so I know what's what. Magnesium is always a +2, and nitrogen, if I look at my periodic table, is always a -3, and potassium is a +1. So in order to put these together, what I'm going to do is go with my outer, or go with, remember, positive comes before negative. And so I'm going to make K with M3. Now this is a -3, so therefore I'm going to need K3 N. That's the only way this can go together. Kn is not a thing. And then magnesium is just on its lonesome now. So it's just written as magnesium. Charge isn't really a thing. Okay, let's balance this. I got 3 magnesiums on one side, so let's put a 3 there. I've got 2 nitrogens right here and only 1 here, so let's put a 2 there. Potassium, I've only got 1 potassium here, and 3 times 2, because I have 2 of these, is 6. So I am going to put myself a 6 right there. Okay, now let's double check. Magnesium, 3 and 3. Nitrogen, 2 and 2. That's good. Potassium, 6, and 3 times 2 is 6. 6. So I'm good. So 1, 6, 2, and 3. Done. Okay, for this one, I want to know, is this going to form a solid? But either way, I'm still going to write out the reaction. Okay, silver is not a variable charge. It's always a +1. If you didn't know that, you can still figure that out because NO3 is in your list of polyatomic ions and it's a -1 and it went 1-to-1 with silver. So there you go. Magnesium is a +2 and iodine is a -1. So let's go ahead and put plus with minus. This is going to go together 1-to-1. So AgI plus positive before negative. So magnesium, which is a 2+ charge. So I need 2 NO3s. So very important that I do that. Otherwise, it's going to be pretty hard to balance this. So silver, there we go. I got 1 on each side. Cool. NO3, I've got 2 on this side. So I'm going to put a 2 here. Yes, that throws my silver off, but I'll worry about that later. Magnesium, whoops. I've got 1 magnesium right here, and I have 1 magnesium here, so that's cool. And then for my iodine, I have 2 here, and I have only 1 here, so let's throw a 2 there. And good news, by doing that, that also balanced the silver. So I have 2 silvers, 2 nitrates on both sides, I have 1 magnesium on both sides, and I have 2 iodines on both sides. So I'm good. Now, will this form a solid? Yes or no? Well, here's what I'm going to do is I'm going to look at iodine with silver, and I'm going to look at nitrate with magnesium. So here's my solubility chart, and iodine right here is usually soluble. So normally this is not going to form a solid. Now, there are exceptions: strontium, barium, lead, and mercury. If this was to have been paired with one of those 4, then that would be an exception, and this would no longer be soluble. It would be insoluble, and therefore, yes, it would form a solid. However, this is paired with silver, which is not one of those exceptions. So this is, in fact, soluble. That's not going to form a solid. Okay, and then my second compound had NO3, right? And I'm fairly sure that was magnesium. Go back and check. Yeah, it was. But NO3, there is no exception. So if that ended in NO3, then it is in fact soluble. So no, this reaction will not form a solid. Okay, this particular one, honestly, I kind of wish I'd put more questions like this on here. I didn't notice I only had 1 of them, so please pay very careful attention to this one. You do need to know how to do this. It can get a lot more complicated, but we're not going to go much further than this right here. So the first step I need to do is I need to do percent to gram. Now, there's a little trick. I can just imagine I have 100 grams of this compound, whatever it is. And if I had 100 grams, then I would have exactly 54.5 grams. So I can just take percent and change it into grams. The justification is the whole 100-gram thing, but that's effectively what I'm going to do. So 54.5 2.5 grams of carbon and 9.2 grams of hydrogen and 36.3 grams of oxygen. Now notice I'm not writing H2 or O2. That's because diatomics, you only use the two when they're not bonded to something. And in this case, carbon, hydrogen, and oxygen are all bonded to each other. So the diatomic nature is not something I need to worry about, but it is something that comes up a lot. So really, really, really important you remember your diatomics. But here I'm thinking about a compound made of carbon, hydrogen, and oxygen. Okay, so the gram, next gram to mole. Okay, so step one, step two. So gram to mole, I'm going to go, remember, whatever my unit is, that has to be what comes down. So grams of carbon, grams of hydrogen, grams of oxygen to mole of hydrogen, mole of oxygen. If I look at my periodic table, carbon is like 12.0 something grams. So I'm just going to put 12, 1. Hydrogen is 1 gram per mole, according to the periodic table, and oxygen is 15.999. So let's go ahead and put a 16 to 1. So in order to convert this, what I'm going to do for carbon is 54.5 divided by 12, and that is going to equal 4.54. Okay, and then 9.2, I'm sorry, yeah, 9.2 times 1 over 1. That's a pretty easy one. That's going to be 9.2. And 36.3 divided by 16, that is going to equal 2.26. Now, this is not a ratio. I can't use this as a ratio. This is just the number of moles I have. All right. So now what I need to do, and this is the easiest one to forget, is divide by the smallest. If you do this, you're going to get your ratio. And my smallest is 2.26. So divided by 2.26, 2.26, 2.26. Okay, and if I throw those into my calculator, I'm going to get like 2.01. I'm going to get 4.07, and obviously divided by itself, this is going to be 1.0. Now, 0.0 something, that's enough. I can just go ahead and round that off. So 2, 4, and 1 is my ratio. So therefore, my empirical formula is C2H4 O1, and I don't write the one, so C2H4O. That's my empirical formula. So make sure you know how to do this. There's 3 major steps: percent to gram, gram to mole, divide by the smallest. Okay, that's it for this unit. So I'm going to go ahead and stop this video here, and then I'm going to come back and do unit 8, which is stoichiometry. So that one's going to have a lot of practice problems on it because there's going to be quite a bit of it on the test, and it's been a while since we've done it. If you have any questions, let me know. But for now, let's go ahead and sign off. So thank you.